Hi everyone, Shalom lekulam. Podcast Al-Halal is very excited to have James Green, NASA's chief scientist with us today. Hi Jim, how are you?
I'm great. Thanks so much for inviting me. We're going to talk about one of my favorite subjects today.
Oh, that is good. And you probably have many. So thanks for finding the time to have this call with us. I'm guessing that not a lot of us have an opportunity like that, so we're very happy for this. I see that we have a lot of people on, so that's very cool. Just before we start, I want to say two thanks. One big thank to the Ramon Foundation and the Horizons team for letting us use their Zoom, because we're poor and we don't have the Zoom that gives you like the Zoom account with a lot of people. So now we do. Thank you. And another big thanks to the Israeli Space Agency for teaming up with us and streaming this event on the Facebook page. So hopefully we have some people watching from there as well. So I think this is the way we're going to do it today. I've asked you to tell a little bit about yourself and how you got to NASA and how you became the NASA's chief scientist. And after that, you'll give us a talk about a very interesting subject, which I will keep secret, and I will let you do it. And tell us a bit about the cool things that you guys are doing at NASA. And then last but not least, we'll have time for questions from the audience. Some people sent questions by email. Some are going to ask probably now in the chat. We're going to try to let you ask, like the audience ask the questions by themselves. So we're going to unmute you, the audience that want to ask questions. Just one thing, one question for one person, because we don't have a lot of time. And if you sent us a question by email, then please change your name on the Zoom so that we can see your full name and we know how to unmute you. So I think with that, Jim, the stage is yours.
All right. Well, thank you so very, very much. Yeah. So you had asked how I got so excited about science, and it really is because of teachers, particularly in high school. And I was in high school in the late 60s. Okay. So what was happening during that time period, of course, is Star Trek, the original Star Trek was on TV. How can you not like that? I watched it from the very first episode. And in addition to that, we were moving towards having humans walking on the moon by the end of that decade. So everybody was anticipating that. And I had an opportunity to work in an observatory with a very large telescope. They had several telescopes, but the one I used was a 12-inch Alvin Clark refractor. So it's a 12-inch aperture with a 15-foot tube, and you're at the other end. And so I did all kinds of astrophotography. I made some photographic instruments on the back, and then I would develop my own film, and I would send some of the images that I took to various magazines like Sky and Telescope, and they would be published. And so when I then left high school, I went to the University of Iowa and started there in astronomy, because I just really got the science bug. Humans were walking on the moon. I was at the University of Iowa, and I was taking classes from James Van Allen, who is our first scientist in the United States with the first successful instrument on Explorer 1. And of course, the large area around the Earth of trapped high energy particles is named after him, the discoverer. And those are called the Van Allen belts. So by the time I got out of the University of Iowa with a master's and PhD, I'd already been involved in a whole host of science missions. And so I got a job at my first job at Marshall Space Flight Center. And then I went from Marshall Space Flight Center to Goddard Space Flight Center, and then eventually to NASA headquarters. So I just got in the space business early, and it just carried me along. So, but as I say, one doesn't start out that way. One is accelerated in that path. And sometimes you even change your directions and thinking. you get what I call a gravity assist as you're propelled forward to finally deciding to become a scientist or, you know, almost anything, an engineer in the aerospace field. So I do enjoy giving public talks, talking about some of the exciting things that we're doing in NASA. And so this is going to be one of them.
Cool. We're delighted. So that's a bit about you. And now let's talk about cool stuff in NASA.
All right.
Do you want to share your screen?
I will share my screen. All right. So today we're going to talk about one of my favorite topics. I have a wonderful opportunity to tell you what's happening in NASA as we go about searching for life beyond Earth. All right. So I brought the NASA secret files with me. All right. I'll tell you anything and everything you want to know. So we'll open up the secret box and we'll go through what we know. And it'll be really exciting, I'm sure, for many of you. The concept that we want to talk about is that when we search for life, we do it as we go out into the solar system and as we look into the sky, but we also do it in time. Time is really an important element of it because right now we are at a specific spot of our evolution of the Earth, where our planets have evolved from 4.5 billion years, and they have changed significantly, and perhaps life existed on those planets in the past. And so we want to look for life beyond Earth, both in space and time. Well, let's start out with the definition of life. So about 15 years or so ago, actually it's almost 20 now, we had our astrobiologists. These are the people that are in this discipline, looking for life and how we would go about it. And we asked them, give us a definition for life, because if we have instruments on spacecraft, what should we be looking for? You know, what's those things that they can measure that tell us, geez, this is life? And after about 2 years of struggling with coming up with a definition, and I didn't want a definition that was just about life like we know it, but a general definition, they came back and said, we've got it. We know how we would define life, and it has 3 attributes. Okay, 3 attributes. First attribute is it metabolizes. So that means it takes in food with water or a liquid, some liquid, and that liquid is used as a solvent, tease apart the energy that we get from the organic material we eat, and then is used to eliminate waste. That's part of that metabolic process. Second thing, it reproduces, and the third thing, it evolves. Okay, and that's the definition, those 3 attributes. Now, they were very happy, and I have to tell you, I was pretty depressed. And the reason why I was depressed is I can't build an instrument that measures any of those, and that makes it really difficult. So if we go into space and we're looking for life, we're going to have to get into a more simpler environment. And that simpler environment then is what are the things around that life needs? You know, what are those ingredients? And so we started with that idea. And for us, like we know it, you know, we have to have water. We have to have food, organics. We're made of organics. We are what we eat. Okay, that is true. We have to have energy. You know, we go through a temperate cycle on Earth where we have to be able to not freeze, but live and survive, and that requires energy. And of course, it's got to have time. And this is the important aspect of time. How long does it take for life to start? What's the spark? And then how does it evolve? How do we get from a single cell, multi-cell to more complex life? And all that requires time, all right? So those are the 3 big basic attributes. So with that in mind, we decided that we'll take this on and follow the water. We'll look for places where water is or has been in the solar system. We'll look at the material that's there, the organics, how much energy it gets, and then model it back and forth in time, okay? And so we can take this and really use it going forward and really look at what we could find out in the solar system. So if we start with Mercury, you know, here's a beautiful image of Mercury from our Messenger spacecraft. And the colors are this is what we call a fake colors, or we're coloring an infrared. Can't see, but we do it in a way that differentiates the wavelengths, and it shows that indeed there's been a lot of material on the surface. Okay, are some of those organics? Yes, some of those may even be organics. However, without an atmosphere, and the fact that it's very cratered and more moon-like, and it's extremely hot on the face, the side that faces the sun, and it's nearly tidally locked, it really is a poor candidate for life. Okay, now we do know in the polar regions, both the North and the South Pole, there's probably water that's frozen in those permanently shadowed craters. Those regions in the North and South Pole where the sunlight can't penetrate. The sunlight can penetrate it, then indeed that water gets released. It gets leached out of the soil. It then goes through a phase change of a solid into a vapor. We call that sublimation. So Mercury, now we know even in time, it's not the right environment. Well, what about Venus? Okay. Well, Venus, you know, was shrouded in clouds, and it really took the space program to really interrogate it and look at it closely. And what we find when we look at the evolution of the planet is there's a huge area that's unknown. It's unknown because we couldn't get the kind of information we wanted. Now, the Soviets actually, during the space race in the 60s and into the 70s, had a series of wonderful missions that actually got down to the surface, made beautiful observations of the atmosphere, and really told us that Venus today is a very harsh environment. So the surface is very hot. It's actually hot enough to melt lead, all right? Very inhospitable. And the pressure, the atmospheric pressure is so great that it's really crushing. It's 90 times our own pressure that we feel here. Now, we can get a feeling for 90 times our atmospheric pressure by going into the ocean and then having the weight of water on top of us, like the weight of our atmosphere is on top of us today. And we have to go several thousand feet into the ocean to be able to get to the point where we have 90 atmospheres, 90 times our current pressure here on the surface. So we know that this is very inhospitable. Now, recent observations have told us that it's also quite hot in certain areas. And when we combine the topography of the planet, which we were able to get through a cloud penetrating radar from a mission called Magellan, we could see that indeed there are a number of hot spots that line up with volcanic domes. So we do believe that Venus is still very volcanic. Now, there's been a couple really important measurements that have been made that tell us Venus has had water in it, even today, but very little. But we can tell by looking at that water, by looking at the ratio of light water with heavy water, that Venus had an enormous amount of water in its past. So what we do next is we then can model it. So here's the time dimension on Venus that we want to do. What you're looking at is the clouds stripped away. And this color rendition of Venus is that the blues and the purples are the low areas, and the reds and the whitish areas are the highlands, all right? So we see there is significant difference in the variation in altitude on the surface. So once we take that ratio of heavy water to light water and know what the heavy water to light water is on Earth and see that it's so different, it can tell us how much water we would use to put back on Venus. Venus was Earth-like. It should have the same ratio of heavy water to light water. So let's make it so. Put it in a computer and run the models, all right? And when we do that, this is what Venus looks like. And now we run those models for millions of years, tens of millions, hundreds of millions, billions of years, okay? And we find out Venus was a blue planet. When, Earth is a blue planet, but Venus was also a blue planet early on in its history. It had an enormous amount of water, and it's only been within the last 800 million years that it has lost its water. Okay, so that means that maybe in its past, Venus had life. So this is really exciting because a recent discovery says, well, maybe there's life still left on Venus if it did have it in the past, but it's somewhere where it's more Earth-like, and that would be in the clouds. Now, there's a certain altitude that's between 50 and 60 kilometers, which is very Earth-like on Venus. And so there's been a set of observations from the Earth that indicate that in this area, we see a lot of phosphine. All right, now that's phosphorus with 3 hydrogens, as shown in this upper right panel. And that is, we think, what we call a biosignature. There's a certain type of life here on Earth. You can actually go into swampy areas, into bogs, and measure phosphine, and it's coming from anaerobic life. In other words, life that doesn't require an oxygen environment like we have, but actually can live in other types of environment that's not oxygen rich. Okay, that's the anaerobic part of it. Now, so this was a discovery not too long ago that we see phosphine and it could be life. So where are we today? Well, that paper came out. A lot of scientists look at it, and there are a couple major problems with that, okay? One major problem is there are, here on Earth, another process that's not life-related that does generate phosphine. And that, of course, is volcanoes, all right? So I don't want to get your hopes up, but right now, the phosphine that we see in the Venus cloud tops may actually be representing a process, an abiotic process. That means a non-life process of generating phosphine in volcanoes, and massive volcanoes on Venus that we do know exist may be pumping this out. So still a lot of work to be done, but indeed at this stage, it's doubtful that this is a smoking gun for life, okay? But that's part of the scientific process. Well, Earth is teeming with life. Earth is still a blue planet from its history, But we really want to tease out what's happened to Earth over time. And here's also the timeline for Earth. It's a planet that's 4.6 billion years old, just like all the other planets in our solar system, including Venus. And after it was created, over time, many different important processes happened to it. It was bombarded. It brought, these things that are bombarding Earth, these near-Earth objects are actually bringing some really important organic material to us. And maybe that was important that provided us an environment for which life could get started. So down along this timeline, we believe life could have gotten started about 3.8 billion years ago, okay? And it's only gotten more and more complex. We've also gone through some really tough times. We've gone through what we call mass extinctions. And in the rock record, we can find 5 major mass extinctions in the last 600 million years, okay? And these were pretty tough events. It's very difficult to find mass extinctions further back, but I'm sure they were there, okay? But this is what we know. And then when we look at the atmosphere and we see the relative composition between carbon dioxide and water and oxygen and nitrogen has changed over time, okay? And that's because the climate on Earth is changing, always changes. It's changing even today. The key is how fast is it changing? We're in an era for which the climate on Earth is changing faster than the humans and many animals, and maybe most animals, can evolve to be able to accommodate those temperatures as Earth becomes more Venus-like, okay? But there's 2 major events that occurred on Earth, these 2 mass extinctions I want to talk about, that were pretty spectacular out of several that I've noted already. And one occurred about 600 million years ago. There's one in the distant past. We don't know much about life in that time period, but we believe it probably is a mass extinction. It's not termed a mass extinction event, but it must have been something similar. That happened about 2.4 billion years ago. Now, what happened? Well, the Earth went through climate change so much that the oceans started freezing, okay? And that means that a veneer of an icy crust enveloped a significant part of the Earth. Well, how much? Well, you can see the geographic extent of these ice crusty areas. More than half the Earth was crusted over with ice, and in some cases, way up in the 80% or higher, the Earth went through these phases, and we call these phases snowball Earth. Okay, and what was happening is the Earth's climate was changing into an ice age. Okay. So a significant portion of the Earth was being overcome with ice. But we lived through those, okay? We passed by and life survived through these climate extremes. Today, we're also protected by extremes in the solar wind because the sun is getting brighter. It also has intense storms. It's always had intense geomagnetic storms. So here's a big storm. It's a coronal mass ejection. And we are largely protected by our magnetic field. Now, Venus doesn't have a magnetic field. At least we don't know if it does. Doesn't have one now. May have had one in its past. And so, indeed, magnetic fields, we believe, are really important to help protect our atmosphere. Now, if we look at Mars, beautiful Mars, and look at its history, we find that in the past, Mars was a blue planet. So at the time Earth was a blue planet, Venus was a blue planet, so was Mars early on, all right? And it also went through climate change. About 3.2 billion years ago, it went through this climate change, making it pretty much the arid Mars we see today, okay? But there's plenty of indication of enormous amount of water on Mars. We now believe, based on several results, but MAVEN, one of our major spacecraft that is orbiting Mars even today, is making the measurements of how the wind ripping the atmosphere of Mars. And so once Mars lost its magnetic field, then indeed that stripping started. And we believe it lost it probably 3.5 or maybe even 3.8 billion years ago. And so it's been sitting in the solar wind, vulnerable over this time period. So that stripping is still going on today. Now, we've landed on Mars, many different places, okay? We have two missions on the way to Mars that will land on Mars. One is the Perseverance rover, and Tianwen is a Chinese lander and rover, okay? In 2 years beyond that, ESA will launch their ExoMars rover, okay? And in addition to that, we expect a variety of orbiters. UAE has a mission on its way also to Mars now that will get into orbit and make measurements of solar wind interactions and look at the atmosphere and even making global observations of the planet. Now, here are all the missions on a Merc section. This is also color coded, where the blues and the purples are really lowlands, and the whites and the reds are high. And when you look at where we land, you see we land in the yellowy, greeny areas, okay? This is the ancient shoreline of Mars. Everywhere where it's blue and even a little bit into the green, it was underwater 4 billion years ago, all right? So this is the ancient shoreline of Mars. And the two missions that are working perfectly right now on the surface are one, a rover that NASA has called Curiosity, and the other one is InSight, which is also sitting in that ancient ocean where it's nice and flat, and it's making seismic measurements so we can understand how active this planet is. So what have we found out about the surface of Mars from our landers and rovers? Well, here is a panorama from Curiosity. And we look at it, and indeed it looks like mud segments, mud flaps, we call it, in an ancient riverbed that's dried up. Wow, that sounds great. And then we bore holes into it. Here are the first 2 holes into the surface. These are the size of a small coin, and they'll go down probably 1 centimeter or 1.5 centimeters, okay? And when we did that, when we pulverized that material and created these holes, we were shocked. We were absolutely shocked. When we look at this, this is gray material. It's not red. It's not completely oxidized. In fact, the oxidation that makes Mars look red is a very thin veneer. But right below that veneer, we see ancient Mars. And what we wanted to do by pulverizing this material is scoop it up, bring it into the rover, and taste it. figure out what it's made of. And what we find is it has all the wonderful ingredients for life. All right, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. The soil is moist, and there are nitrates in the soil. All right, and nitrates are a great fertilizer. And of course, having moist soil is really important. So I often get asked, if you've seen the movie The Martian, can we grow things in the soil of Mars? And at the end of even this first indication and tasting of the soil, the answer is yes. All right. So it's got all the right stuff. Now, we may still have to bring fertilizer, but indeed, Mark Watney, you could grow things in the Martian soil. Now, the rover that's on its way right now is called Perseverance, okay? Named by one of the school kids in the United States. And it's got a fabulous suite of instruments from many different countries, in France and Spain and Italy, and also Norway. And so these instruments are going to really help us tease out much more of the structures and the mineralogy, looking for signs of life. Now, one of the top things it's going to do is actually core rock. You know, so it's going to bore a hole into the surface. If my camera is still on me and you're seeing me, let me just show you what one of these cores look like, okay? So here's a core. This is done with the engineering unit before we built the flight unit. And it's about the size of a piece of chalk. Now, many in your audience may not know, the younger crowd, what a piece of chalk is, but maybe a large Crayola creme, all right? And then we put it in a container, metal container, and we accumulate several of those and then sit them on the surface for later recovery. Now, where we're going is a place called Jezero Crater. And here's Jezero in the upper left corner. When you look at that, man, it looks like an ancient delta. And in fact, it is. It's a river flowing into this crater. And this crater occurred on the ancient shoreline. And so in reality, this crater filled up with water, broke the other side, and flowed into the ancient ocean. So this is just a really exciting place, because all that material over many hundreds and hundreds of miles on Mars will then tumble down that sediment and come into Jezero Crater in this delta area. So we're really excited about going there and looking at it and taking a look at it. Well, how do we bring the samples back? Our plan is to create several launches, okay? Another launch will happen from Earth. You see the cruise phase landing, and there it is. It sits on the surface, and what that is a Mars ascent vehicle. We'll then have a rover pick up the samples and bring those samples in these metal containers to the Mars ascent vehicle. Then in the far right side, we will erect that rocket, launch it, and then the samples will be thrown out and put in orbit, for which then another spacecraft will come down, pick them up, and bring them back to Earth. Now, the samples are really important, okay? They tell us all kinds of history of Mars. Hopefully we get some samples that will tell us a lot about how the climate changed, okay? As I told you, we don't know how fast that change occurred, whether it occurred over 100 million years or 10 million years. But how do you go from a blue planet to a complete desert world is really hard to fathom. And maybe that rock record will tell us. But there's some other important things about rocks and their minerals. When we think about Earth, there are 5,000 minerals on Earth, and 300 of them can only be created by life. So the rock record can indeed tell us a lot about the past of Mars and whether there could have been life on the planet. That is a real smoking gun. That data will be quite concise and quite obvious to us. Okay. Now, what's really exciting is Mars actually still has a lot of water, but the water is trapped in various locations. We know there's a lot of water underground. In fact, we've been finding now underground aquifers of water, liquid water. Okay. Now, the polar cap, here's the North Polar Cap. Okay, this sits in the ancient ocean of Mars, in that North Pole. All right, and when we look at it, it looks from a spectral point of view like carbon dioxide. Well, that's what dominates the atmosphere of Mars. So during the winter in the northern polar cap, it snows carbon dioxide snow. But we now know what's underneath that carbon dioxide veneer. It's water. And so when we take a slice of this, as shown in the bottom part, lower right, this is a ice penetrating radar. We see the stratigraphy. We see the massive snowfalls. And it's huge. You know, it's more than 1,000 kilometers across. And it's 100 kilometers or more thick. And so it turns out that when we look at the volume of water underneath that CO2 veneer, it looks like it is about 1/7 of the ancient ocean. So a lot of that then got trapped. Well, what's going to happen over time? You know, we've talked about the past a lot. We know what the future is like too. The sun will continue to increase in intensity. This area will then heat up, and that means the CO2 veneer will sublimate. It will go back into the atmosphere. And CO2 is a great greenhouse effect. In other words, it holds heat in. And because Mars's atmosphere is very thin, it's holding heat in, but not a lot. If you increase that significantly, you then can increase that temperature. So as the sun's temperature increases, CO2 sublimates, heats the atmosphere. We also expect some of that water ice to melt and become liquid water. And so as we project forward, what would Mars look like? We believe it will bounce back once again into being a blue planet. All right. Now, it's not going to have the ocean it had in the past, but it will have a water. And this is tremendously exciting. And therefore, you know, maybe ancient life that could be hibernating there will spring back. We don't know. We don't know. Now, this will take several 100 million years, all right, unless we can figure out a way to enhance the greenhouse gases on Mars and bring it to us sooner. And there's a number of ideas on how to do that. So let's look at our terrestrial planets in terms of the history of them. And we do that in this diagram, and we call Earth now in a habitable state. It's in the right area, receiving the right amount of energy. It has the right materials. It's got everything going for it. So we're well situated in that habitable state. And on the y-axis, this is the age of the sun. So we are at 4.6 billion years since the sun started heating the entire solar system. And so we can categorize our planets as they are today. Venus and Mars are too hot. Venus and Mercury are too hot, Mars appears too cold, and the Earth appears to be just in the right place. Now, when we think about the evolution of Mercury, never had a chance, okay? Didn't really have much of an atmosphere ever. And even though it has some of the right materials, it has too much energy. It's too close to the sun, all right? But what about Venus? Well, Venus, as I mentioned, was a blue planet in its past. It rapidly evolved to be that blue planet. But then over the last 800 million years, it moved out of the habitable state. Well, what about Earth? Well, Earth went through two major cycles called snowball Earth and almost popped out of the habitable zone, okay? Life indeed survived through this time period, but just barely, all right? Well, what about Mars? Well, we think Mars, habitable in its past because it was a blue planet the same time that Venus and Earth were, and now it's too cold, it's too arid, but indeed it may evolve back into that. So once again, we're thinking then of looking at these bodies in terms of how they've evolved over time. Now let's look in the outer part of the solar system, and if we go out to Jupiter, we find the spectacular moons, the Galilean moons, okay, first observed by Galileo. And what's really great about these is they were all made at the same time, but they look all different, okay? So you look at Callisto. Callisto's just full of craters. You look at Ganymede, not as many craters. You look at Europa, it's very hard to find craters on Europa. You look at Io, and there's no craters on Io. In fact, what you see on Io, when you look at it in the infrared, are active volcanoes. So Io, as a body, is resurfacing itself about every 80 to 100 years. You'll need a new Google map of Io. It's really turning itself inside out. Now, how is that possible? Well, that's because Jupiter is tugging on these planets. When you think about all these moons, planet-sized, I mean, they're huge. They really go through tidal forces. So they're in elliptical orbits, which means there's a part of the orbit that's really close to the planet Jupiter. Jupiter squeezes it, and then as the body moves around Jupiter in the other part of its orbit where it's further away, that squeeze is less, all right? And so what's happening, if you just look at the planet, is it's being squeezed and released and squeezed and released. And that heat has got to go somewhere. On Io, it's turning itself inside out. However, Europa still has an icy shell, but indeed, we think it's in what we would call a habitable zone. It may be in a habitable state. There may be life on Europa. So let's take a look at Europa in particular. These cracks are cracks in the icy shell, all right? So Europa has a thick icy shell, but what's underneath that icy shell is water. Now what's happening is as Jupiter is pulling and squeezing, it's actually melting that ice and creating an undercrust ocean on Europa. And in fact, when we look at the amount of water we expect, there's perhaps twice as much water in this undercrust of Europa ocean than there is water in our ocean. All right, so this is an enormous amount of water. All right, so this is really good news because it's been that way for 4.5 billion years. All right, so that means it's got plenty of time. So we think it has plenty of energy from the tidal forces. We think it's got plenty of water. Look at that ocean, it's enormous. We think it's got all the right organic material. and it's got the time. So here is really a perfect place to go, and we're launching a mission called Clipper in just a few years that will go to Europa, orbit Europa, and really interrogate it. Well, what about Saturn as we move further out? Saturn also has some spectacular moons. And here's one. It's called Titan. Now, Titan is enormous. It's bigger than the planet Mercury. It has an atmosphere mostly dominated by nitrogen, but has a lot of methane and ethane and other trace gases, significant amount in reality. But what's really exciting about this body is that this has about twice the atmospheric pressure than the Earth does. And that means when we actually can land things on Titan that are a certain mass size or certain mass range with parachutes all the way down to the surface. And that's what ESA did with our partnership, NASA ESA's partnership. We're using the Cassini mission. They had a probe called Huygens that went all the way down to the surface. And then we had a cloud penetrating radar that took a look at the global moon, Titan. And here's a segment that we saw that I want to talk about. This is a spectacular set of observations below that atmosphere, peered right through it. What the blue and the black area is very laminar. So it's very, very smooth. And we now know what that is. It's liquid. So indeed, Titan is the only other body in the solar system that we have found that has liquid on its surface. But it's not liquid water, it's methane. We also know that Titan's got tons of the right organics. It's just a hydrocarbon delight, okay? And so now we're thinking, well, if we want to think about life and those three things, metabolism, evolution, and cell division, what about that metabolism? It needs a liquid. Maybe that liquid could be methane, all right? So that means if we look for life on Titan, maybe it's life not like we know it. We haven't found that, but we have a new mission going. It's called Dragonfly, and it will land and interrogate Titan and look for signs of life. Now, as we look out into the solar system, beyond our solar system, and look at other solar systems, one technique we've used, here's the Kepler mission, is the transit technique, where as we stare at a distant star, if there are planets and they're lined up in such a way, they could actually pass between us and that star. And if they do, they actually hide a little bit of the starlight. And so if we just look at the starlight over and over again, just measure the intensity of light, all of a sudden, if it goes down and comes back up in a pattern like this, and does it repeatedly, over several what would be orbits, we then can tell a lot about planets in that solar system. So the time it takes for the curve to go down and go back up tells us how far away that body is. The depth of that curve tells us how big the body is, okay, how big the planet is. So when we do that with the Kepler data, we see this kind of distribution. We now believe, okay, from Kepler data alone, there are more planets in our galaxy than there are stars. Okay, so that means on the average, you look at a star, it has at least one planet and maybe more. And so consequently then, here's the distribution of planets. We want to know what's the average planet. Now, this was a shocker to me, and it was because I always thought, well, it's got to be these big ones. It's got to be like Jupiter or Saturn. Turns out that's not true. In fact, there's a range, sort of a mid-size that really is the dominant planet. And so you see here Mars-sized, Earth-sized planets, and then you go up in scale, super Earths and sub-Neptunes. Most of the planets around other stars are bigger than our Earth in terms of being more massive. And in size, more massive also means a little bit bigger, okay? And they could be gaseous envelopes creating Neptune-sized bodies that are also observed. So though that was kind of a shocker that the preferred planet is a super Earth or a sub-Neptune. So what are these super Earths like? Are they all terrestrial? Yeah, we think they're terrestrial in the center. We also think they may have a lot of water, depending on where they are. So there may be huge oceans. Imagine a world that's completely an ocean, okay? It's almost like Europa without the ice crust, okay, but close enough to the sun where the ocean could exist. So it'll also have an extended atmosphere. Or it could have a very thick atmosphere, okay? Maybe an atmosphere that's more Neptune-like, where it's more of the primitive gases that are captured and retained from our collapsing nebula that created our solar system. We call that a primordial atmosphere. Well, what's next? Well, for these kind of bodies, we need to interrogate them and look at the atmosphere with our spectral capabilities. And James Webb, it's going up, will be able to do that. It's going to look in a range that is a perfect spectral range to determine if there's all sorts of complex organic and carbon molecules. So it's like CO2 and methane and also water bands. So indeed, this is a perfect way of thinking about looking at the spectra to determine if there are what we call biosignatures, signatures that maybe life is generating these kind of complex organic gases. So that's really exciting. Other types of biosignatures, we would be looking for an excess of methane. There could be indications of vegetation. These are all kinds of biosignatures. So by looking at our Earth and understanding what our biosignatures are in the same spectral range is what we do when we're going to look at the atmosphere of other planets from the Webb telescope. Okay, so at night when you go out and you look at the stars, okay, what you're not seeing with your own eyes are the planets, but they are there. And in fact, these are some of the brightest stars in the northern and southern hemisphere. And these orbits that are around these stars are indeed the planets, those solar systems that we now know exist around these stars. So it's a really completely different view and an exciting one. Okay, so let me end by answering, have we found life beyond Earth? Okay, and the answer is no, not yet. But we have found all kinds of important signatures that may be aspects of life, not only current life, but perhaps remnant life. Certainly, we have found environments as we look at the past in time where life may have existed. It may have come and gone. So this is really an exciting time. I think we're actually maybe less than 10 years away from answering the question, is there life beyond Earth? Okay, very exciting times. And so with that, let me thank you and take any of the questions you may have. Thank you very much.
Thank you very much, Jim. Very, very interesting. We do have some questions that were sent to us by email, and then we're gonna take some questions here from the crowd. For some strange reason, I can't see the chat here. So if you have a question, there is an option to raise your hand. You can, I think, click on the 3 buttons on your name or something like that and raise your hand, or there are reactions down here. So at the bottom, there are reactions. Raise your hand and we'll get your question. We'll unmute you. Aviad, you want to start with the questions we received by email?
Yeah, thank you. So by email, the question, first question, 2 kids. We are Neta and Itamar from Israel, and we are 6 and 8 years old. Just a moment. Okay, we want to be scientists and astronomers at NASA when we grew up. How can we become astronomers and scientists at NASA? What do we need to learn?
Okay, really great question. So with me, as sort of an example, you know, I just followed my interest. I followed my passion. I got really excited. I thought about science. It's an exciting era, and we're running into another tremendously exciting era. NASA's going to land the first woman and the next man on the surface of the moon in the South Pole by 2024, and we're on track to do that. So soon we're going to see some really exciting things going on, just like the Apollo program. Now I can tell you that it's so inspirational because I saw it. And I saw it on a black and white TV that was fuzzy. You know, when we land on the moon, you're going to see it in high definition, and it's going to be absolutely spectacular. Okay? So follow your dream. Follow your dream. Study hard. There's a couple things about it. In my mind, I was good in math and science, but I wasn't good in all aspects of math. And yet I am a scientist. You know, you're going to run into some problems. I hated geometry. Okay, I'll just fess up. I hated geometry. You know, I couldn't wait to get out of geometry. But, you know, give me a differential equation and I can analyze it. But bottom line is, you know, as you go through your career and you study and you learn, you're going to have ups and downs. Don't give up. Be determined. Be determined. That's the best thing you can do. Now, in terms of working for NASA, that may be possible. But to me, what's even more exciting is all the space agencies that are coming about, okay? Israel has a space agency. It's doing all kinds of things in space. And over time, it will increase its importance in space. And so you have a wonderful opportunity to work for your country, for your space agency, and for humankind in your country, because a space environment is a critical vantage point. From that, you can look at, you know, what is happening in the country in terms of climatic disasters, or you can look at how much land is under cultivation and understand that you need to export or import food based on what you find out. The advantage of space is so tremendous that we're seeing now many countries entering into that arena. So I would say it's not necessary to work for NASA. You have a wonderful opportunity right there in your own country.
Okay, thank you. Tal Gorin is asking, do you expect the space sector to be more accessible to the public in the coming years?
Yes, I do, because indeed, as I mentioned, the space sector is doing an enormous amount for the people of the world. The key is, fortunately, in the 60s, we created in our treaties, like the outer space treaties, that we would use space for peaceful purposes. And we want to make sure that continues. We want to make sure that countries respect that and indeed enforce that, because that will be critical as we move forward. I also believe that we are going to the moon, and we will go there to stay for decades as we learn to live and work on a planetary surface, and then also go to Mars, all right, and begin to live and work on Mars. Mars has all the right stuff for us to be able to think about starting or colonizing that planet in the long run. I mean, we are at a really critical juncture of mankind, humankind. Mankind is also the other word we use, but everyone moving out into space for peaceful purposes. And that doesn't mean abandoning this Earth. It means also having the opportunity to explore together the solar system. You know, the solar system is absolutely spectacular, with many bodies that we can go to. And we need to go there together. And now that many other space agencies are coming, beginning and growing, we indeed want to be able to embrace that. In fact, we know, NASA knows, that going to the moon, it's not going to do it itself. It's going to do it in a partnership. And so we've written a series of what we call accords. They're called the Artemis Accords. And 7 countries just signed that this week, that were extremely important. And these are all about working together for those goals.
Okay, thank you very much. Last question from the internet. Guy is asking, what do we think about SpaceX? Will it be dominate company in the space industry?
Yeah, so SpaceX, we're really excited about the commercial sector, for which SpaceX is one of several companies. What I think has been confusing for many people to understand is NASA, since about 2005, so for the last 15 years, NASA has worked hard to encourage, even provide funding, startup money for a whole variety of commercial companies, including SpaceX. Now, why did we do that? Well, we think there's a space industry that is waiting for us to move into. You know, so what's happening? Well, on Space Station, we see so many spectacular things going on. From having an environment where gravity isn't the dominant force, where pharmaceuticals can be made, where we can understand changes in biology based on zero gravity, that gives us an indication of how the body repairs itself in ways that we can't tease that out here on Earth. I mean, there's just a whole host of experiments that we do in space now on Space Station that many of the commercial environments can pick up. And we want that to happen. So as companies want to use space stations, we don't want them to just necessarily call up NASA and say, NASA, we need a rocket. We want them to buy their rockets from the commercial sector. Mm-hmm. Not only that, we want to buy those same things to those commercial sectors, and we're doing that. You know, we now have astronauts that have made it to Space Station that are non-NASA employees. They're commercial. You know, there's a whole line of commercial astronauts, but but we've now have commercial rides for our astronauts. We just did that. We had 2 astronauts that were taken up by SpaceX, and we want to continue that. You know, we want to continue to have not only NASA astronauts in space station, but non-NASA astronauts too. So that's very important for us, and that commercial sector is really, really coming on, and they'll be important partners for us.
Okay, thank you very much. Now Sharon Perlman want to ask something.
First of all, good evening, and thank you so much for this fascinating talk. I'm Sharon, and I'm running an international space community called Our Space. And what I wanted to ask is, until we find an alternative planet for us, what is NASA doing operatively, actively regarding global warming to reduce the carbon footprint in the atmosphere?
Okay, so NASA is an organization that makes the key observations. All right, so we monitor the globe not only in terms of water cycle, all the major weather systems that occur. We are using our satellites, and the weather industry is getting access to that data and the models and predicting hurricanes, etc. NASA is looking at carbon footprint. We have 2 major systems up and running that do global carbon dioxide monitoring. You can get access to that data, so we see where all the carbon dioxide is coming from, and we can model where it's going to go. And we are the ones that have worked with organizations like NOAA, the National Oceanic and Atmospheric Administration, to be able to monitor and model climatic change over time. So a couple things about climate change that's really critical to know is climate on Earth has done nothing but change, is going to continue to change. If you look over the history of humans on this globe, cultures have come and gone because of climate change, all right? So we are in an era where we are gathering the data that is used for the policies to understand our approaches to either accepting or changing or modifying how humans are creating a variety of what we would call greenhouse gases. What we know about climate change really started on Venus. So the top scientific modelers that determined that Venus had a runaway greenhouse effect brought their codes to Earth. And that's why we know the role carbon dioxide has been playing as it's increasing not only its content, therefore it also increases its ability to hold heat in causing our climate to change. So there's a whole series of things that are going on in terms of technologies that are being developed for which NASA data is being used, all right? We talk a lot about, how countries are generating CO2, and we want to limit those CO2 amounts to a certain amount. And that's really hard to do because we are still largely using fossil fuels that the end result produces more CO2. But in reality, we have a whole series of ways to take CO2 out of the atmosphere. For the last 20 years, we have had humans in space, on space station, a constant presence. And what we do each and every day is we take CO2 out of the atmosphere. If we didn't do that, they'd be dead. Okay? So there are all kinds of different techniques that are being explored that can reduce CO2 by what's called carbon capture and then sequestration or reuse, and many companies are involved in that. That's a really promising industry. Now, NASA's not doing that research, I mean, it does it in space because it needs to. But what we learn and how we do it can be applied by many other industries. And of course, we want to make our data available so that people understand, you know, where in the world the CO2 is being generated, how much is being generated, and what happens from the models of that generation. So did that answer your question?
Okay, thank you.
I think we're close to 8. It's a quarter to 8, and I see that we have more questions that we got on the email and more questions here. So let's try to ask the quick questions and have maybe
quick answers.
Short,
you're really talking to me.
True.
You're not talking to them. You're talking to me.
No, I don't mind. I don't mind
All
if
right,
we stay
okay.
here until 8:30. Doesn't matter.
Okay.
It's your time.
So Jay Howard wants to ask something. Jay?
Yeah, sure. Hope you can hear me. I'm actually calling from my car. It's almost like a spacecraft. I just set on a mission here to pick someone up in isolation. So I put up plastic wraps. But in any case, on the topic of isolated life, and I've heard in a previous talk of yours, but now about there could be places like Europa where the climate has not changed for like billions of years. So could there be life there which exists and is stable and even technologically advanced and more advanced than humans, for example, but not so interested in seeing us? What do you think?
Good question. So the water environment is really intriguing to us because we believe that maybe life started on Earth in our ocean and migrated to the land. And so although we recognize Europa is a great place where it's got all the right stuff where life may have started, we don't know if it's just if it is life, whether it's a few cells or small amoebas or more complex. But the fact that it has time, to me, means we should not be surprised if we find complex life underneath that ice crust. So the tough thing is, how do we do that? And so Clipper is going to go there, really fly through plumes of water that pour out from these cracks and take the water from the ocean and put it on the surface. This is why Europa doesn't have any craters anymore, because they filled them in. You know, it's modified the surface. It's taken that water in the ocean and put it on the surface and destroying the craters. So the surface of Europa is young. We also think the surface of Europa, we see a place where there's subduction going on. That means one plate of ice is moving under another. Spectacular. You know, this is the kind of environment that would be just perfect for life. Now, let me say, we have not found life at Europa, all right? But if there's any place to go where there might be life today, that's my bet, that there might be it there.
Okay, now Dr. Roy Yaniv want to ask something. Roy?
Hi, hello. First of all, it was a great talk.
Thank you.
It's a privilege for me as an atmospheric and planetary scientist to ask you a question. And my question is, if we went to the moon in the 60s with a very low level of technology, how come that we haven't reached to the moon yet? To the moon again and to Mars, because the technology level today is very, very high compared to what it was. So what have we done wrong?
Well, so it's like being in a candy store, okay? If you like that kind of candy, why are you eating this candy over here, okay? And so that's really what happened to the agency. After we went through a period of exploration of the moon, it took us actually decades to really understand what was happening on the moon. We brought back 850 pounds of moon rocks, and we're still creating exciting things of knowledge from those moon rocks. Still. And so in the meantime, while we really had a richness of things to do and analyze, the decision was we really needed to explore low Earth orbit more fully. We really needed to enhance our Earth science program. We really needed to do a better job of monitoring and understanding resources here on Earth. We needed to figure out climatically what was happening over time. We needed a platform like Space Station for us to be able to develop what now looks like a very promising future business industry in space. All right. So the hiatus of all these years has really taken us in a different direction. But now we're ready to go forward to the moon. We don't like to say go back. We like to say go forward. And that's what the Artemis program is all about.
Okay, thank you.
Thank you. Now, Nika, want to ask something? Nika? Nika once again. Nika, are you hearing us?
Yes, do you hear me?
Yes.
Yeah.
Well, I am 15 years old, and my dream from childhood is to become an astronaut. And my goal is to see or maybe participate in the expedition to Mars in 2030. So I wanted to ask you, you think that the steps that I should reach this goal?
Okay. So what's critical is that you take time to figure out what you're really good at, what you really enjoy doing, and then turn your attention to that. You know, many of the astronauts are good in different areas. They're good in, some are good in science, some are medical doctors. You know, and the different types of science, from astrophysics to planetary science to geology. And so I want to say, learn as much as you can in school, but find your passion. Figure out what that is that excites you, and then go do that, all right? And then as opportunities to come up that you might end up becoming an astronaut, go for it. Go for it. And what you know and what you have learned and everything that you can bring to that is then available to that agency that picks you up and says, you're going to be our astronaut. Okay, so have at it. Be determined. Don't give up. All right.
Okay, thank you very much.
Aviad.
Yes. Yes,
I see there is Bobby Shitz.
Yeah, Bobby Shitz.
Oh.
This is
Unmute
exactly.
him.
Yeah.
All right.
Okay.
I have a question about is there any option for a project for biotopia on any planet, like the moon, of being one?
Okay. Is there any option for in that? And you cut out just as as you were. Say that again, please.
Is there any option or projects or being projects on biotopia on the moon or any other planets, like?
Okay. So when you say biotopia, you mean colonization?
Also.
Okay, so our plan is to do something very different than we did with the Apollo astronauts. So the Apollo astronauts got down on the moon and stayed for a very short period of time. You know, they weren't on the surface more than 3 days. Apollo 17 was less than 3 days, and that was the longest stay. Okay, our plan is to stay on the moon not only for a few days, but for weeks and maybe for months. Okay. And so we're now developing plans where we'll need habitats. We're going to look at resources. We're going to figure out now how to live and work on a planetary surface. So we're just trying to figure those things out right now. In the meantime, we're looking at Mars. The planetary scientists are gathering together and they're looking at Mars to figure out, where should we land on Mars? Where should humans go on Mars and explore the planet? And our concept is that we'll go to one place. We'll call it an exploration zone. It's about 200 kilometers in diameter. We'll land in one area. We'll live in another area. will use resources on Mars, but will also explore that area and do a whole variety of different science. So right now, scientists are working on those projects right now. So it's at a very early stage. So by 2030, we hope to be able to know where we're going on Mars, know what we'll be doing, and begin the planning process of flying humans there and landing them and living and working on Mars.
Okay, thank you. Parat want to ask something? Yes, Parat? Okay. Yes. Unmute.
Okay, hi.
Hi.
Thank you for the talk, by the way. I would like to know what is NASA's main goal now that commercial companies are taking over the market for space launches and landing on the moon, for example. The Artemis missions are supposed to be more commercial than the NASA's things. So I'd like to know what is NASA's main mission currently.
Yeah, so that's a good question. So what we're doing is NASA's typically been involved in low Earth orbit. You know, we talked about space station. That was a multi-agency activity. You know, but they were all space agencies. Now we have commercial entities that want to use it. So while we leave space station to do mostly commercial activity, that's where they will be. We're going to move out to the moon and then to Mars. So NASA's not given up developing rockets. We now are developing the space launch system that will take us to the moon and then on to Mars. So it is a very powerful rocket. It's 10% more powerful than the Saturn V, which was a spectacular rocket that got the Apollo astronauts to the moon. So our goal in NASA is to start the process of exploring with humans our solar system beyond low Earth orbit. So Artemis is a NASA project. It's not a commercial effort. It's a NASA project.
Thank you. Roy Chen.
Yeah, hello. So thank you for the talk.
My pleasure.
Do you think that humanity will ever build a Dyson sphere or a Dyson swarm? And if so, when?
Okay. So to build anything, and particularly a Dyson sphere, which is so huge.
You want to maybe explain what that is?
Yeah, go ahead.
So it's basically like a megastructure that we can build around our home planet, like the sun, and basically gain all of its energy for our own usage.
Yeah, it provides some neat ideas and neat flexibilities. However, it's not. We can't do that in a practical way. It's gonna require a need for us to be able to move in that direction. Now, there's nothing wrong with testing segments or doing some things in an experimental approach, and perhaps some of these commercial companies that will go into low Earth orbit and be able to do things at space station will want to try some experiments. But I don't think we'll be able to do it in my lifetime, and it might be, you know, hundreds of years before we say, hey, we need it, we'll build it.
But you believe like someday it will be possible? That when the need will be raised?
Yeah, so never underestimate the ingenuity and the ability of the human race, okay? It sounds like a grand idea, you know, but it may indeed be possible, not today, but in the future, particularly if there's a need for
it. Jim, it's 8 p.m. right now here in Israel. Do you have more time? Or
I do. Yeah, let me answer 3 more questions. How's that?
Cool. Let's do that.
Your time.
Hi, I'm 16 years old, and I was wondering, I know if you feel like you've already answered that, then it's fine, but like what career path you should go if you want to work at the space agency? Because you said something about following your dreams, but it means like a little more specific to like the things you have to study and the stuff you have to do.
Yeah, right. So if you want to end up being a scientist, you know, you really have to pick a discipline, and there's so many to choose from. That's why, you know, your passion, you really got to say, this is the kind of science I want to do, and then concentrate on that. So science typically relies on a variety of tools. Those tools are mathematics, computer science, even more so than ever, AI technologies. Now, those are also key to engineering. And engineering is very different. It's applied science. It's the ability to take what we know about materials and phenomena and express them mathematically, that then can create and develop new and important things. And if that's what excites you, hey, great. Now, I've been involved in some instruments, but I know I'm stronger as a scientist than I am as an engineer. And so that's my passion, is in the science area, is acquiring data, analyzing data, and then publishing scientific discoveries. That's what excites me. For instance, there's nothing more exciting to me than uncovering something that no one on this planet knows, but it's important to know. That's what science helps do. And that's a real rush. Okay, it's a real rush. And once I do that, I want to do that again, and I want to do that again. That's following your passion. If you have that in a particular area, that's what you want to do. So step back and say, what do I really like? But I would encourage you to, you know, take a broad set of courses and things to find that passion, so that you really know this is it, and I want to do this the rest of my life, because it is the rest of your life. You want a job you like. I love my job. I come to work every day. You know, whether I commute from the bedroom into my study, or I drive down, you know, to a building or in the laboratory, which I hope to be able to do someday soon. But indeed, I look forward to that every day, and that's the kind of job you want.
Right. Thank you very much.
Three more fast. Ariel Cohen.
Thank you for a great talk. And I have a specific question about the results of the Viking spaceship.
Yes.
That were inconclusive, and there is a big controversy over whether or not there were any indications of life.
Yeah.
So first, I wonder why none of the subsequent missions actually tried to replicate these experiments. And would Perseverance try to do this?
Good question. So let me just briefly say there are three main life detection experiments on Viking. And without going into the details, the project and the scientists got together and they said, we will declare we have found life on Mars if each experiment gives us a positive indication. Okay? Out of the three experiments, one experiment called the label released experiment, they got a positive indication, but the other two did not. So following the rules that they'd established, they decided they couldn't declare that they found life. Okay? That's what they decided to do. So your question is, why haven't we flown those experiments again? And the answer is, we get the same answer. So because we don't want to replicate the same answer, okay, we'd be in the same dilemma. So let's do something different. Let's bring the samples back. We can perform the same experiments on those samples as we did on Mars, but 1,000 other experiments that then says what we found is life or isn't life. So this actually is the next big step in that area. So in reality, finding indications of life when you don't know the kind of life you're looking for, whether it's like us or not like us, is really hard to do. And you have to be able to say what those indications are and build on that knowledge to then create the experiment or a series of experiments that are definitive. And they all build on each other. So we now know what those experiments have said, and now we're moving beyond that. Okay, Ariel, does that answer your question?
And this is something you can't do there. You have to do this at home.
I wouldn't want to do it there because we did it already. Why would I spend $6 billion to do the same experiment?
No, these additional experiments that we're going to do.
The additional experiments would be bringing the samples back. Now we have them here, so we can perform the same 3 experiments, but we can perform other experiments that tell us and inform us why the experiments gave the results that they did.
Thank you. 2 more quick questions. Asteroid mining.
Yeah, hi everyone, and thank you very much for the talk. I enjoyed it very much.
Great.
My question is about asteroid mining. What do you see about the horizon of that? Is it feasible? When will it happen?
So it's feasible. Yeah, that's right. I think it's feasible today at some level. But is there a drive to do that? Well, right now, there's not a huge drive to do that, although it's important. I think it's going to be an important thing to do in the future. The first element of that, though, would be mining on the moon. All the asteroids that we have out there that we've studied and we know about, they've all hit the moon. And so asteroidal material is all over the crust of the moon. So by going to the moon and actually doing a variety of mining there will be very much like mining asteroids, I predict. Now, what's important is some of these areas have a significant amount of iron, and therefore they have some platinum group metals. And we're mining platinum group metals here on Earth, and in a matter of a few hundred years, those will all be exhausted. So if there's a desire or a need for more platinum group metals, the first place to go is the moon. And then the next place to go is beyond that into the asteroids that are crossing our orbit that we can get to that may have some of those materials.
So Artemis.
Yeah, so Artemis is our first step to be able to get humans there, for which some of the experiments are going to be to really look at the mineralogy, to determine what minerals are there, whether there are a lot of metals or other things that we can extract and use even while we're on the surface.
Thank you very much.
Mm-hmm.
And last but not least, we say in Hebrew, אחרונה חביבה, Lior H.
Hi, thank you for this talk. I would like to ask about your job with a lot of scientists. Of course, you can't drill down to every discipline. So how do you do this? How do you know what questions to ask and how you work with a lot of people that each is an expert of something?
Mm-hmm. Okay, yeah. So you may not know it, but I'm a magnetosphere physicist. Okay, that's my discipline. I never met a magnetic field I didn't like. Okay, so the magnetic field of the Earth, the magnetic field of the giant planets, even Mars had a magnetic field and lost it. Why? In fact, yesterday I have in Advances of Science a paper that I published. I'm first author on it about the magnetic field of the moon. What did the moon's magnetosphere look like? Okay, just came out yesterday. So those are that really excites me. That's my expertise. But I also recognize there's so many other things that I need to know. I need to know geology. I need to know planetary science. I need to know how asteroids come together, create protoplanets. You know, protoplanets come together to create a major planet, how the planet differentiates, how you create from an conglomeration a crust, a mantle, and a core, and then what in the core actually generates the magnetic field. So all these things are related. And therefore, over time, I've just gotten excited about several other parts of our science. And of course, finding life, you know, what's not to like about that question? And that's being done by a number of spectacular scientists, astrobiologists. And that's another discipline that was created when I was already doing science on magnetospheres of Jupiter. You know, I wasn't an astrobiologist when that came around. So these new fields that are coming up are just really exciting, and astrobiology is one of them. So
I guess the bottom line is curiosity.
Yes.
Be curious, right? And to ask, not to be afraid to ask a lot of questions.
Correct.
And then you'll get the answers from other people and you'll get smarter.
Yeah, there's I mean, we always think, oh, this, you know, I don't know why I don't know this. Well, I got news for you. There's an enormous amount of stuff I don't know. I ask questions all the time, but nobody thinks I'm stupid. So, you know, we all have things in our experience space, and they're not all the same. And this is why it's important to ask questions, have dialogue, and understand what's happening. So, so remember, no such thing as a stupid question.
Wow, Jim, this was amazing. I'd like to thank you very much for this talk. And I'd like to thank everybody that participated. I don't think we have a lot of opportunities to have talks with people like you, so thank you.
I have one last thing I'd like to say.
Yeah.
Okay. So, pardon me. I have a podcast, okay? It's called Gravity Assist. And it's in its 4th season, okay, 4th season. And this season is all about the search for life beyond Earth, all right? And so I talk to all kinds of scientists, you know, that are really doing detailed work where some of the exciting things are coming out that won't be in textbooks for decades, okay? That I want people to know about. And so if you're really excited about what I talked about today, please go to Gravity Assist and learn a lot more.
I'll put that in the link with the video and everything.
Super, thank you.
Great, so thanks again. Thanks for your time. I also want to thank my podcast team, Aviad Man, the Superman that does the sound that was with us now, and Itai Leon, Donko Leon that does all the design, and Bennett and El that does all the proof checking and all the social networking with us. And I think that's it for today. I'm Eyal Ben-Zaav, and this was another episode of Al-Halal. Thank you very much, everyone.
Thank you so much.
Thank you, Jim.
My pleasure. My pleasure. Take care. Have a wonderful evening.
Thanks.
Bye-bye, everyone.